Okay, hi everyone. So I guess almost everyone who is interested is here. I'm Pierrick Bouvier. I work at Linaro in the QEMU team. I joined like 1 year ago, and it's the first time I come to KVM Forum, so I'm happy to meet all of you here. So today I will talk about the single binary project we have been working on. So I will mostly answer to these questions in that order. So first, what is the single binary? So what we're trying to do is to create a single QEMU system binary that is able to run several guest architectures. So right now you are used to have different binaries in your build folder, and we would like to experiment to have a single one that can emulate several of them. As a first step, we only want to emulate one architecture at a time, but our long-term goal is to be able to mix several architectures together, as I will explain later. Two things are important to say. The first one is that we are not trying to do this work for the user mode binaries. So basically, we are only targeting the system code and the generic code in the QEMU code base. And we absolutely don't want to replace the existing binaries. There is no hidden plan to change everything, at least not right now. Maybe once all architectures are included, we could revisit this. But for now, we are just trying to do something new that may or may not work in the end, but it should not impact how you are working and what you are used to. So why do we need that? So as I said, our goal is to be able to emulate platforms that are mixing several architectures. This is what we call heterogeneous platform and heterogeneous emulation. So the use case is mostly to model some boards that have a main processor, microcontrollers, DSP, or any other kind of accelerator, and be able to emulate all that in a single QEMU process. Two examples of those boards are, for instance, a SoC, the Qualcomm Snapdragon X Elite, that has a main R64 CPU and a Hexagon DSP, and another board that is already present in some parts in a QEMU code base is the Zinc UltraScale. So basically, this one has a main R64 CPU, an MCU that is 32 bits, and as well a PMU that is controlling the whole thing, which is a microblaze. Right now, the UltraScale board is present in QEMU if you try to emulate that, but we only have the ARM part on one side and the microblaze part on another side. So the goal here would be to be able to run all this in the same process, to model more accurately how hardware works. So why do we want to make a single binary? What are the other alternatives? So the first alternative that is already existing and that the AMD folks are using is to mix several processes. So basically you have one process per architecture, and you add plumbing with IPC and stuff like that to communicate and synchronize the states. Of course, it can be something complicated and it can be costly to make this communication as well. But I know some people are working this way and it's working pretty well. Another issue is that it's something that will be harder to upstream because it's quite an exotic setup, even just for launching the whole thing, etc. So that's why we are exploring the single binary. Another natural route we could follow would have been to use shared libraries because one of the problems is that we cannot link all the code together because of symbol duplication and stuff like that. The problem is that the QEMU architecture is not, it's not bad, but it's definitely not good enough to do that. We have too much interdependency between the components, including target and generic parts of the code base. So this is a problem. And so in the end, you can only create fat shared libraries with a lot of code inside, including the generic part. So you just reproduce the problem you have with the multiprocess. This is what we tried first, by the way. So we went this way. So to come back on the QEMU architecture, to explain a little bit more why we cannot have shared libraries, this is like what you would expect. So if you have a QEMU system binary, it's using the lib system that is using target code, and all this code is using a common library. It's not exact, but I'm just trying to give a big picture here. And we more have this in reality, like basically, so it's not as much spaghetti code as that, even if we're in Italy, but there are definitely interdependency that make that, for instance, if you need to link to some symbol that are provided by the target libraries, and so you cannot choose selectively which symbol you want in which target library by design. Another word about the QEMU architecture. So just to say that QEMU was historically designed to run a single target, so it's not really a surprise that it's hard to do anything different. It was from the build system to the way the code is written, it's really assuming that you will run a single target. So it used heavily the preprocessor. And talking about the C preprocessor, it's definitely a very good solution if you want to handle host configuration. So when I talk about host configuration, this is what is related to your host machine, your OS, the CPU where you are running QEMU, and not the target you are trying to emulate. For me, the problem is that right now in QEMU, the preprocessor has been used for target code as well, and this creates a lot of configuration that are pretty subtle, and that needs to, so you need to recompile the same file several times with different flags depending on the flavor you want for your QEMU. And it's something that can be a problem. You will need to duplicate compilation unit, code can be harder to follow, and definitely it's impossible to do any heterogeneous simulation like we are trying to do. So really, if you work on that in the future, I will encourage you to use more the build system instead of the preprocessor. So basically, you create a proper interface, and you just select which proper file you want for a given architecture, compared to just duplicate a C file with different flags. Finally, another thing, we have some places in the code base where things are written in a way to provide more performance or to guarantee dead code elimination or stuff like that. That's very nice, but those days you can rely on LTO with your compiler as well. So if you really want extra performance before hacking your code architecture, just check if it's really relevant, and if you cannot get that for free with LTO, before polluting your architecture. Yeah. So this is the why. Now I will talk about the different steps we are following for the single binary. This is not exhaustive. If you have more questions, come to see us after. I just try to give a big pictures of the thing so you get an idea of which kind of work we did. So the first thing is that to make this project work, we need to have an iterative approach, because we need to touch a lot of code, either target code or various QEMU subsystems, and it's definitely impossible to do everything. We cannot send a single series with everything. And even if it was the case with the commands and etc., it will be hell to keep it alive for long enough. So definitely we cannot work this way. So we tried to find an approach that is better, and we decided that we would start with the ARM and R64 target, because this is what we maintain at Linaro, so it's easier to merge code in this part. And then later, once we have this first proof of concept, we can expand it to other architectures. So what we're doing mostly, as I said, is to remove the target-specific parts in the different files of the code base, okay? So mostly we try to eliminate most of the if-def and stuff like that related to one architecture, to change that to runtime checks and paths, etc. I will give more example later, don't worry. And another important thing is that since we have to do that for a long time, we must make sure we don't regress, because if we fix some files and people reintroduce target-specific stuff all the time, it's endless. So for that, we are using config poisoning that I will present as well after, which was already present in QEMU, and that is very, very convenient for that. So on the build system side, what we have been adding is a new common library. So the one you can see on the bottom left, the common ARM, for instance. So this library holds the code for ARM and R64, and any file inside it is compiled only once. There is no duplication of compilation unit. And this model works pretty well. We can replicate that with all over architecture in the QEMU code base. And thanks to that, we can have all the object files present only once, at least for our ARM proof of concept. And finally, to track our progress, because we want to know how far we are from our objective, we are using this script. It's not very important, the command line, but the point is that we can find, thanks to the compile command JSON file that is generated by Mason, we can find how many files are duplicated and in which folder they are, and this is how we targeted our work. At the end of the presentation, I will give you some statistics, and you will see the progress we did, and it's definitely based on this command. So once we will have finished for a proof of concept to deduplicate all the compilation unit, which we didn't do yet, spoiler, we will have to make sure that we can link all these object files together. So basically, we will have some conflict at symbol level. So first we work at file level, eliminated the duplication, and then you need to link, so symbol level. It will not be a big problem because we already anticipated that, and we even took a look at it. Mostly when we have a symbol that is provided by different architecture, different targets, you can either extract a proper API, you can write a dispatcher function, so basically the symbol exists only once, and you manually say, if my target is R64, I call the R64 flavor. If it's ARM, I call the ARM flavor, x64, and PPC, and all over stuff. Or you can use stub if you need or not the symbol. All that is already present mostly in the code base. There is nothing really new. Yeah, we are just reusing what exists. Another very important thing is to not break existing binaries. As I say, we don't want to disturb any of your workflow or break anything. So the first part is that we must make sure that we don't compile once a file that contains target-specific code. So we would eliminate some configuration in a hidden way. So for that, we rely on the config poisoning. So if you look at the two headers I put here, you can see it's a list of identifier that I marked as poison, and if they are present anywhere in your C file or your header, it will be a compilation error. So you cannot reintroduce target specifics because the target identifier are automatically marked as poisoned. We have something similar for system versus user because there are some specificity I will not explain, but we took care of that as well. Of course, we don't want to change the command line interface. We will have to add a new option. I will explain that later, but we will add that to the existing binary as well. So your command will work with the single binary or the current binary, no difference. We don't want to change the possibility to restrict the list of targets or to use kconfig to create a strip binary that really tailor just your needs. So all that will be supported. There is nothing specific. Just a word about the binary itself to give, I don't know if you will get it or if I explain good. Basically, it will just be a recollection of the existing object files. So by that, I mean that we will link together object files that are already present in any of the QEMU system binary. So we are really not generating new object code. We are just linking them in a different way, and all the transformation we made before ensure they can be linked together. So there is no new binary or what. It's really just a new way to link all the things together, and it should work, yeah. And as you see, like we have a patch on our side, we can just build it with the Ninja command I put here. It will not be built by default, at least as long as we don't have all the architecture ported. And finally, to not break existing binary, we must make sure that we don't add any performance impact or that we don't increase the code size in a crazy way. We don't have any automated test suite for that. There has been concern sometimes, especially on some specific points. So if you have concern, really feel free to ask us. It's part of the work to show that it works and to make the necessary benchmark or stuff like that. We did that so far, and every time we didn't really observe any difference at all. Yeah. But yeah, since we are mostly changing things from preprocessor, so at compile time to runtime checks, yes, there are new branches and stuff like that, or new indirection if you add a new interface and all. So it can be costly if you are on a hot path, but we didn't see anything critical so far. So now we'll give more concrete example of the work we did. So probably you already saw this kind of code in the code base where you have if def a specific target, I will do something specific, else I will do something else. So this is how we hope to replace that. We already have all these functions upstream. They are already there. So as you see, it's pretty straightforward. There is nothing specific. The only difference, as I say, is that it will be evaluated at runtime and not anymore at compile time. And as well, we provide a single target info header. So it's a new API that allows any code in the code base to poke those information easily in a generic way without having, without having to include any target specific header. Yeah. So nothing really complicated. Another thing that was a bit more challenging is to deal with the target-specific hardware, like basically the board definition, the CPU definition, and any kind of a specific device that belongs only to one target. So for that, we found that the best way was to use the QEMU object model. So for the people who are not familiar with it, it's like an object type system, similar to any object language you would know. And we are using the possibility to implement some interfaces to tag the various devices with the target they support. Okay? This is what people would call tagging interface. So this interface is just empty. It has no method. It's just an interface name. And it's just a way to put in the type system, okay, this device, you can see it, for instance, if you are with an ARM target or R64 target. And it scales very well. Like we tried that. It's not really a big issue, the same. In QEMU, where before the main, some things happen, and part of them is to register all the COM types. So it's just a big hash table, and you have a static constructor that are just adding that to this table. So in the end, we will have more types in the system, but it's definitely not something that should be measurable. And if one day it's a problem, we can always try to optimize this part and all, especially when we will have all the architectures linked together. And of course, on the target info header side, on the new API side, you can poke, you can retrieve those type names, so for the board name or the CPU name, and something similar for other devices that we will implement later. Now we are able to link everything together and to select which device goes with which target. We must be able to detect or choose the target at runtime. Okay? So once again, we use the QEMU object model. So we will just add a new type target. This is not done yet. Just to tell you, don't look for that in the code base. It doesn't exist. So we will add a new type target that is the same as type machine or type CPU. So nothing fancy here. And as you can see in the patch part of the slide, we can just easily retrieve all the targets. So if only one target is available, then it's pretty unambiguous. You know what you are running. If you have several, you need to have some heuristic to detect it. So the most natural heuristic that is used by Clang, for instance, which has the same kind of behavior, is simply to make some matching based on your binary name. It can be a symlink or a binary. Of course, we want to give the possibility to user to override this default target. So, for instance, the dash target option could be a natural candidate. And this is, if we add that, we will definitely add that to the existing binary. So, if you run the existing QEMU system R64, you will have only one target embedded, which is R64. And if you use the same command line with the single binary or the QEMU system R64, it should work. Like, you should not have to modify your script or stuff like that. And I know there were some concern as well about the heuristic concerning the binary names and all. We will really do our best to support if you are used to rename your binaries or stuff like that. Of course, there is a limit and a compromise, but we are really open to make any kind of detection. It's done only once when we start the program, so we can do something fancy and complicated. It's definitely not a problem for performance. In more than everything I said, there are some additional benefits, like unexpected benefits. So the first one is that we simplify the code base. Mostly, first we started by doing a lot of cleanup in the generic headers and all. So it's something that is hard to measure, but we think it's cleaner now compared to before. We will remove a lot of if-def, so it will be turned into runtime path. Some people could argue, is it really more simple or not? Yeah, it's something we can talk about. But we will remove the if-def, so less build configuration as well, which is better. It opens the possibility to do some code coverage analysis. You can do that now, but it's quite confusing for most of the tools like LCOV, stuff like that. When you have functions that are present in different places in the code base, they really don't like this. So if you have a single way to compile a given file, the code coverage tool cannot be confused. Since we are decreasing the number of compilation units, of course it will be faster when you compile several targets, and you may have smaller build folders. For instance, now if you compile all targets, it's 9,000 compilation units, and if I remember well, like 4,000 or 5,000 of them can be factorized, so that's a lot. And finally, it will bring better support for your completion tools. If you use auto-completion, you probably already reached the wrong function when you were editing a file. This is because one file can be compiled in 20 different ways, and your editor usually just takes the first occurrence. So since we work on the system code only, it will not remove the confusion between user and system part. But if you compile only for system, hopefully you will reach the function you expect more easily. A quick word about heterogeneous simulation. It's absolutely not the topic today, but I just want to say that there are additional challenges. Once we have the single binary for the architecture we target right now, we will have to do more stuff. It will not work out of the box. So we already identify a few things. The problem right now is that it's impossible to experiment because we cannot have the binary itself. So we can only imagine problems or imagine solutions. We cannot really implement them. So we really want to stay focused on the single binary. It's really a prerequisite. And the heterogeneous will come after that. And as well, in the long term, I really want to say that I think it will be best if we keep the promise to not break existing binaries. So we will not add a new binary. It will just be the QEMU system binary that will support stuff. Or maybe we will add the board to the existing QEMU system R64 or MicroBlaze binaries. We didn't really decide yet, but I think we should all keep in mind that it would not be such a good idea to create yet another way to do things because QEMU command line is already quite complex, so we can try to keep it coherent with what exists and hence the existing command line to support the new use case instead of just saying, okay, I have a new binary, I do what I want. So when all this will be ready? So for right now, we are trying to target 10.2 or 11.0, I should say, for ARM plus R64. So this first proof of concept is not really interesting feature-wise because if you take the QEMU system R64 binary, you can already run 32 or 64 bits boards. It's not really needed to have a single binary. But all the work that we do architecture-wise and build system-wise, they will be really used for all of our architecture, and this will scale in the long term. So once we have this first thing that will be upstream, it will be very good news for the rest. Once we have the ARM and R64, we want to add MicroBlaze, so we can model the ultra-scale board I mentioned before with all its components and not only the ARM part or the MicroBlaze part. And right now for the 10.1 release, so most of the non-target code is unified, so all the generic files or files that don't belong to a target have been unified mostly. We've done all the subsystems I put here, so the MMU, TCG, thanks to Richard, the FPU, Peter, plugins and QAPI, thanks to Red Hat guys. And we will merge very soon the interrupt controllers for ARM, the semi-hosting and the migration as well. So it's definitely work in progress. You can see on the right of the page Between 9.2 and 10.1, you can see the list of the folders in the QEMU code base that have duplicated files. So the number is how many duplicated files there are. And basically, you can see the work we already did. So we did a good progress. And more important, that you cannot see it in the slide, but we really tackled the biggest issues we had in the first place, which was the hardest problem we had to solve. And so, yeah, once we have our first proof of concept, we'll be able to explore new solutions for the heterogeneous emulation. And we'll definitely make other talks about that in the future. And yeah, so if you are interested for the heterogeneous stuff for your own company or your own needs, really come to talk with us, because we already heard a few things right now, but we are not aware of all the use case for heterogeneous simulation. Maybe you have things we don't know, so really come to talk to us. It's really nice to get a good big pictures of things. And so who is working on that? So first I want to say thanks to Philip, who has been working on the single binary effort alone for a very long time, like 2 years. We joined him in the start of the year, the rest of the team, so things really accelerated. That's nice. And as I say, we will work on ARM and R64 architectures, so you are really welcome to do that for your own architectures if you want to work on x86, or if you want to work on RISC-V or PowerPC or any other, even old architecture. You're really welcome, and we can talk with you to explain or suggest different approaches, so you don't have to rediscover all the problems by yourself. So really don't hesitate to send us an email, or we can talk. And that's all. Thank you very much. Yeah. And time for some questions if you have. Yes, Thomas? Yeah, so right now, basically, we all have our own tree mostly. At some time, we have been unifying things either in Peter tree or in Richard tree, depending when we work on, but we don't maintain a downstream fork with everything. Yeah. And right now, we don't really have a lot of series in flight, like the one we have already been posted. We realize that if you develop too much, it gets really hard to manage all the series. So it's easier to go slow and accept that it takes time to upstream them, yeah. Yes?
Me? Okay. I didn't fully understand why you need to tag the devices with the architecture type.
Basically, we have some device, when I say device, I mean something defined in hardware folder that belongs only to one architecture. For instance, you don't want the geek to appear for anything else than ARM code, yeah.
I mean, it might not work, but who cares?
Yeah,
why not?
Yeah, or maybe why not? It would be possible, but I think it would be better that you flag that explicitly. You say, okay, this device is really supported for all architecture or this list of architecture. Like basically, it comes back to the premise to not break things. To make it simple, when people list the devices, the CPU or the board, we don't want to see any change. It could be acceptable to get a change, it's not a wrong thing, but we don't want to say by default, hey, you have to take everything, if you are not happy, it's the same. It's really not the thing. We are very conservative on that. That's the reason. Okay.
Yes. Yeah. Don't create accidental interfaces. We have too many of them.
Yes.
My question, have you observed an impact on compilation time?
So I didn't really try to benchmark the whole thing. As I said, if I remember, we already removed maybe 700 compilation units or something like that. Yeah, so it should be faster. The files are simpler as well. So yeah, I mean, it will not be twice faster, but it can be. It's always smaller and faster anyway. Yeah. And it's not the main goal. It's just an additional benefit. Yeah.
Yeah. Not really a question, more of a note or a reminder. Please think of how libvirt will be able to figure out what the new binary can do and
yes.
introspect what targets are available and that kind of stuff.
Yeah, so basically, we didn't send any patch for the target option and stuff like that, but definitely it's something we want to make proper to make sure it works, yeah.
Thank you. So is there a specific reason why you want to leave out user mode, or is it just too much work, let's do it later?
Yeah, that's mostly that, yeah. It
Right.
just focus on one thing and do it first, yeah.
Perfect, thanks.
But it would be super nice to have a QEMU user binary that can emulate all the architectures. I think no one would say it's a bad thing, yeah, so.
So for QEMU user, there are some restrictions with the ABI for the binary, so we will need to have a few ABI. Maybe we can restrict the set of QEMU users to a subset of ABIs, but I don't, maybe using share libraries, but we will likely have a lot of still user binary for some time. We cannot have just one single QEMU user binary. Richard, maybe you can confirm.
The primary problem with userland is the system call emulation and the structure variation between the different architectures. So I don't see a easy way to clean that up quickly.
How does adding different targets affect the binary size overall? I'm wondering whether like adding every architecture makes the binary size going like close to twice more, or is it insignificant?
So basically, as I say, if you consider that roughly half of the compilation are duplicated, mostly if you combine all of them in a single binary, you will have 50% of the smallest size of the smallest binary, plus the difference added by each architecture. I don't know how much a fat binary would be, maybe 150 or 200 megabytes, but just saying the number, don't take that for real. No, it's mostly the concern for code size, like for instance for ARM and R64, we expose more register and more function. So, and you compile that anyway. So basically, even the QEMU system ARM binary gets a little bit bigger because it has new function and stuff, yeah. And sometimes they were over concerned. It was like 1,000% size increase, so it was not really a big deal yet. But if you are concerned with something, really, we are super open. It's not a wrong thing to ask, quite the opposite.
Yeah, 200 megabytes sounds.
I just want to clarify, so we are keeping the kconfig configuration, so if you want to build the same binary, if you target S390 for example, and you build QEMU system with the kconfig for S390, you should have almost the same that QEMU system S390 now. So it should be no difference.
Okay, thank you everyone, and if you have any other question, come to see us, okay? Thank you.